Welcome to A-Level and AP Physics. In today's lesson, we will discuss some important past paper questions on electricity and radioactivity from May-June 2022, Paper 1, Variant 1. In this lesson, we will discuss some typical type of questions about electricity and radioactivity. And we will discuss these questions in detail so you can have better understanding of these questions, and also you can improve your conceptual understanding of these two topics. Let's study together, let's improve together. For question number 36, it is given to us the sum of currents entering a junction in an electrical circuit is always equal to the sum of the currents leaving the junction. Why is this? So we need to justify this one. Let's try to understand what is happening at any junction in a circuit. At any junction in a circuit, the amount of charge entering the junction has to be equal to amount of charge leaving the junction. Simply we can say number of electrons entering a junction has to be equal to number of electrons leaving the junction. Simply we can write down this one: sum of charge entering a junction has to be equal to sum of charge leaving the junction. So we can say Q out. They have to be equal. But if we divide this one by T, if we divide charge entering a junction by T, and if we also divide charge leaving a junction by T, so we can say this is divided by T. So Q over T, this is equal to current. So we can say this is I in, means sum of currents, means total current entering. This one will be equal to total current leaving. Total I leaving means sum of currents leaving a junction. So that's reason current entering a junction has to be equal to current leaving a junction, because this is based on conservation of charge. So this is based on conservation of charge. So this is simply conservation of charge. Conservation of charge. Current entering the junction has to be equal to current leaving the junction. It is based on conservation of charge. So the answer for this question is A. It is consequence of the conservation of charge. So our answer for this question is A. For question number 37, it is given to us in the circuits shown the temperature remains constant. In which circuit does the potential difference V increase with increasing light intensity? With increasing light intensity. So we can write down here first of all light intensity. Light intensity. So when light intensity increase, potential difference increases. We need to find out that circuit. So in this case, we need to understand this component is thermistor. So we can also write down the names of the component. Thermistor. And this one is LDR, light dependent resistor. And this one is common fixed resistor. This is also LDR. And this one is thermistor. This is LDR. This one is thermistor. Now we need to understand, if you look at circuit 1, in this case temperature remains constant. If temperature remains constant, it means the resistance of this thermistor will remain constant. So this resistance remain constant. So it means that if light intensity increase, there will be no change in this potential difference, because resistance of this one is constant and resistance of this one is also constant. So there will be no change on this voltmeter reading. Now if you look at option B, in this case, when light intensity will increase, resistance of LDR decreases. Resistance of LDR decreases when light intensity increases. So we can simply sketch, let's say we have resistance, this is for LDR, and here we have light intensity. So you can understand better what is the shape of the graph. So in this case, if we sketch a graph between resistance and light intensity for LDR, you will see the shape of the graph is like this. So as the light intensity is increasing, resistance of LDR is decreasing. So if resistance of LDR decrease, so this potential difference also will decrease. So this is also not possible answer. Now if we go to option C, in this case you can see Same situation, resistance will decrease if light intensity increase. So resistance of this one will decrease if light intensity increase. So if light intensity increase, resistance will decrease, so the voltmeter reading will decrease. So this is also not possible answer. Now if we go to option D, in this case we need to understand, as light intensity will increase, resistance of this one will decrease. Resistance of this one will decrease, so potential difference, or we can say if we connect a voltmeter across this one, the reading of voltmeter will decrease. But in this case, EMF of the battery is fixed. So we can say the VT means this is potential difference across thermistor, plus we can say the potential difference across LDR. So when light intensity will increase, the potential difference across LDR will decrease. But EMF of battery is constant, so the potential difference across thermistor in this case will increase because temperature is constant. So this reading will increase. So our answer for this question is D. So this is how you can approach this problem. For question number 38, it is given to us carbon 14 decays into nitrogen 14 by emitting a beta minus particle. Which statement explains why the beta minus particles are emitted with a range of kinetic energies? First of all, we can write down this nuclear reaction. So in this case, we have carbon 14. So carbon has atomic number 6. And its mass number is 14. It decays into nitrogen 14, means mass number of nitrogen is 14 and atomic number of nitrogen is 7. And in this case, beta minus particle is emitted, and also there will be electron neutrino, anti-neutrino, electron anti-neutrino, because this is electron. This particle, beta minus particle, this one is electron, so this has to be anti-neutrino. This is simply, this one is electron and this is electron anti-neutrino. So in this case, energy released in this reaction, this energy will be shared between these three particles. So some of the energy will be taken by this. The least amount of energy will be taken by nitrogen because this is very heavy nucleus, so its speed will be very slow, and rest of the energy will be taken by these two particles. But when we look at kinetic energy of beta minus particle electron, we observe always in the same reaction kinetic energy of beta minus particle, or simply you can say electron, that was different. So then we thought there must be an other particle that is also released with nitrogen 14 and also beta minus particle, because before this was not discovered, neutrino was not discovered that time. So then scientists, they start thinking about this one, why energy of this particle every time is different, kinetic energy every time is different. Then there was a theory about this one, that there is an other particle, and that particle was neutrino. In this case is electron anti-neutrino. So this is how neutrino was discovered before it was detected. So before detection, theoretically we discovered there must be another particle, and then later this neutrino was detected as well. So neutrino was discovered before detection. So the kinetic energy is shared between, mean the energy released in this reaction is shared between these three particles. So we can write down is shared between these three particles. So this is what you need to understand. Now if you look at different options, if you look at option A, carbon 14 nuclei have slightly different masses. This is not possible answer. The emitted beta particles have a range of different masses. Mass of electron is fixed, so this is also wrong. The energy released in the nuclear process is different for each carbon 14 nucleus. Total energy is the same. but energy is shared between these particles. So this is also not possible answer. So answer has to be D. The energy released in the decay process is shared between the nitrogen 14 nucleus, this nucleus, beta minus particle, and anti-neutrino, electron anti-neutrino. So the answer for this question is D. Very historical event in physics, how neutrino was discovered before it was detected. So you need to understand this is due to beta decay. I hope it is clear to you, and very important question. For question number 39, it is given to us a nucleus of a radioactive element emits an alpha particle, then a beta minus particle, then another beta minus particle. Which statement describes the final element that is produced? Imagine that we have nucleus X, and this nucleus X decays into nucleus Y by emitting one alpha particle and by emitting two beta minus particles. So in this case, we can also assume atomic number of X is C and the mass number of X is A. Now we need to find out what is mass number of Y and what is atomic number of Y. In this case, we can simply understand that A is equal to something here, and this is the mass number of Y, plus we have 4 and plus we have 0, because mass number of beta minus particle is 0. So this one has to be A minus 4. So simply we can say mass number of Y, this is A minus 4. Now we can also find out atomic number of Y. Atomic number of Y, simply you can see this decreases by 2, and here we have minus 2. So due to this one alpha particle, atomic number of Y will decrease by 2, but due to beta minus particle, atomic number will increase by 2. So it simply means that atomic number of Y is the same as atomic number of X. As atomic number is the same, it means element is the same. So it means X and Y nucleus, they belong to same element. Atomic number is same, it means same element. Atomic number is also equal to proton number. So as proton number is not changing, it means these two nuclei, they belong to same element. As they have different neutron number, or we can say mass number is different, so they are isotope of same element. So they are isotope. So if you look at option C, it is given to us, it is an isotope of the original element. So the answer for this question is C. Rest of the options are not possible, so the answer is C. For question number 40, we need to find out how many hadrons, baryons and mesons are there in this given nucleus. First of all, let's try to understand what are hadrons, what are mesons, and what are baryons. Hadrons we can classify into baryons, and we can classify into mesons. Baryons, they consist of 3 quarks. Means the particles, if it consists of 3 quarks, that particle is baryon. And if particle consists of 1 quark and 1 antiquark, that particle belongs to mesons. Now if you look at this nucleus, for this nucleus we have mass number of this nucleus is equal to 9. It simply means that this is equal to sum of protons plus neutrons. So simply we can write on protons and neutrons. And this nucleus, it consists of 4 protons and it consists of 5 neutrons. Now we need to understand proton, it consists of 1 down quark and it consists of 2 up quarks. So this is composition of proton. And neutron consists of 1 up quark and it consists of 2 down quarks. So it means proton and neutron, they consist of 3 quarks. So it means proton is a baryon, and neutron, is also baryon. Baryons, they belongs to hadrons. So this is subclass of hadron. So we can also say proton and neutron, they are also hadrons because they belongs to hadron family. So neutron is also hadron. So this is also hadron. So in this case we have 9 hadrons. We can simply write down. So we have hadrons 9 and we have baryons also 9, but we have number of mesons equal to 0. No meson because they do not consist of quark and antiquark. So the answer for this question has to be C. We have 9 hadrons, 9 baryons, but no meson because they consist of 3 quarks, not 2 quarks. So the answer for this question is C.